Hello. Hi everyone. Panam for anyone that speaks Welsh here today. I'm Paul. Today we're going to be talking about functional programming in Python. Just as a show of hands, so who has experimented with functional programming before? Many? About half, cool. And in Python particularly? Not so many. Okay, cool. So hopefully this will be a little bit informative then. Hopefully this catches up. Cool. Yeah, so what I want to go through today, so an overview of functional programming core principles and why we might want to use them, how we can implement them in Python, and then take a quick look at Coconut, which is a Pythonic functional language. So who am I? Paul Jones. I'm a software engineer for Capgemini UK, based in Bristol and working in London at the moment. I'm a Python and Java developer, doing more of a DevOps role at the moment, so deploying cloud-native applications to AWS using Kubernetes and Docker. And my first experience of functional programming was via Scala, so experimenting with that, and then that led me down into thinking, well, how can we implement this in Python? So, apologies, but if we take it back to basics and put this all in perspective. So, what are our main programming paradigms? So we've got imperative programming, where the code tells the computer what to do step by step. It's manifesting computation in terms of statements that change program state. Procedural, which allows code to be grouped into functions and tested and maintained. Logic, which is mathematical logic to represent and execute programs. And then alongside all these we have functional programming, which is computation, where computation is evaluated of mathematical functions and avoids state and mutable data. So Martin Odersky, who wrote Scala, deems object-oriented programming to be orthogonal to all these. Obviously the idea of grouping code and data into data structures. But we'll revisit this right at the end and put it all in perspective in terms of how FP and object-oriented programming can coexist. So in particular regard to imperative programming, so imperative programming is oriented around modifying mutable variables, assignments, and control structures. Imperative programming is limited by the von Neumann bottleneck, so this being the latency between reading and writing data between the processor and memory. Imperative programming conceptualizes programs word for word, which becomes a problem in scalability, since we're dealing with data structures at a too low a level. Functional programming languages in general tend to focus on defining theories and techniques for working with high-level abstractions such as collections, polynomials, and documents. Therefore, let's start to concentrate on defining theories for operators expressed as functions, avoid mutations, and have powerful ways to abstract and compose functions. So what actually defines functional programming? So there's various definitions, but in general, we can say that functional programming is orientated around immutability, removing assignments, loops, and other imperative control structures. It's composed of first-class functions, so functions which accept other functions as arguments or return functions. This facilitates code reusability and abstractions. Pure functions, functions with no side effects. Side effects are any actions which perform any piece of code that affects the state outside of that code. Immutable variables and objects, so obviously once set we can't change them. So languages like F# support immutability in the compiler. However, in Python we have to use other methods to enforce immutability, which we'll have a look at in a bit. Lazy evaluation, so only do computation when results are needed. Many benefits such as reducing memory requirements and saving unnecessary computations that may never be used. Recursion is a big one. So an alternative to iteration, which it eliminates and reduces the use of loop variables. So tail recursion and tail call optimization can be implemented or simulated in Python using a technique called trampolining, again, which we'll come on to in a bit. Pattern matching, which simplifies type checking and object element extraction, whilst reducing the need for extra variables. So all these factors aid in concurrency, mitigating the von Neumann bottleneck. So John Carmack said that in a completely pure system, race conditions are impossible. So we can derive from this that this is good for exploiting parallelism and for multi-core architectures and cloud computing. So going into individual components of FP. Purity is one of the main components. Pure function is essentially any function that can be represented as a mathematical expression only. No side effects, so we have no I/O, no global state changes, no database interactions. The output of a pure function is dependent on its inputs, so arguments in, results out. So the same input always yields the same output. It should be simple. They do one thing, they do it well. so similar to dry and the signal responsibility principles. They take a limited number of arguments, so preferably 0. Any greater, and we should probably start looking at refactoring. State should not be modified. Functional language cannot eliminate side effects, though. They can only confine them. Since programs have to interface with the real world, some parts of every program must be impure. So the goal is to minimize the amount of impure code and segregate it from the rest of the program. As we've got there, so it leads to fewer bugs, more testable code, and code reuse. So going on to first-class functions, so you treat functions like any other object. You can assign them as variables, pass them as arguments, get them returned from other functions. These are epitomized by inline function definitions with anonymous functions, as we can see with lambdas. Higher order functions. So aided by first-class citizens, higher order functions take a function as a parameter or return functions as results or both. This facilitates, again, code reuse, underpins partial application and currying, which we'll come on to next. So in this example, we've got a top-level function which takes another function and 2 parameters, calling the given function with A and recursively calling itself with any new arguments. Then we define 3 pure functions, which are just calculations, and then we have 3 functions, each with different function parameters, which then sum the results. So moving on to partial application. So this is the idea of pre-populating arguments before they're called in a function. So simple example, we just add 2 to the parameters and assign that to a variable. We call that again with another parameter 5, and then we add 5 to that result. And then currying. This is the idea of transforming a function that takes multiple arguments to be called as a chain of functions, each with a single argument. Applying the first argument gets a function returned, and then applying the second we get the result. So immutability. So this is quite an interesting one when it comes to Python. So obviously we never modify the value when we assign it after we've instantiated it. Leads to fewer bugs, more maintainable code, and aids in concurrency. Flexible code can be thought of as feed-forward data flow. So this is the idea of we never come back to change the value of a variable. Hence why data always moves forward from the inputs to the ultimate outputs, from one function to another. Also, immutability leads to referential transparency. So this is the value of an expression can be the same anywhere it might occur in the program, as long as the required variables are defined. Since values are never updated, they mean the same in any context once defined. This ties together with pure functions, as there are no mutations or side effects. We always know what the function will return. The benefit of not using assignment statements is quite obvious. If we never have a concurrent update problem, you will never have to update anything. Since functional programming languages do not have assignment statements, programs written in these languages don't change the state of very many variables. Mutation is reserved for very specific sections of the system that can tolerate the high ceremony required. Those sections are inherently safe from multiple threads and multiple cores. So the bottom line is that functional programs are much safer in multiprocessing and multiprocessor environments. So when it comes to Python, so out of the box, there's no way of defining immutable variables like we would use in other languages like final or const. However, we can use immutable data constructs to help us here. So in this example, so we start with a dictionary inside a list, obviously, which is totally mutable. So we can reach in there, we can pull out values and change them, and we can delete entire entries. If we want to start to introduce elements of immutability into this, we can wrap that in a tuple, and then we've still got a mutable data structure, but at least at the top level, we've got things that can't be deleted. However, we have to be careful when nesting mutable constructs in immutable types, as whilst the state of the outer type cannot be modified, the inner list is can still be changed, so we can reach in and actually change values in that. Moving on with that example, so to start we have an immutable named tuple with properties, so these are no longer fields but pretty much keyword arguments. We assign a new instance of the employee object and the elements become immutable, so we can't just go in and get name and change that. We build up these lists of objects, and while we can't mutate the state of the individual employee properties, we can still delete entire entries, however. So the solution of that is again to wrap it in a tuple, which makes this data structure immutable. The last example, we can define a set, so we can't delete, but we can call add and remove into these functions. So instead we can use something called a frozen set, which ensures the set is immutable, stopping deletion and modification to the state of the set. So moving on to recursion. So another core principle of functional programming, iteration is not provided within functional programming, therefore recursion facilitates iteration. This eliminates and reduces the use of loop variables. Any iterative code can be converted to recursive code. It is always better to implement tail recursion when writing functional code, which can be simulated in Python using a technique called trampolining, which we'll come on to next. Tail recursive code is easily optimized into iterative code by the underlying compiler, making the compile code more efficient. So now on recursion within Python. So Python has a built-in recursion limit, which prevents infinite recursion causing overflow of the C stack and crashing Python, so that's around 1,000 iterations. A recursive function is tail recursive when a recursive call is final execution of the function, so this avoids stack recursion. And like I said before, Python doesn't optimize tail calls, but we can use a technique called trampolining. So, as we said, we don't have tail call optimization with no plans to add it soon. The reason being, it's perceived, is that TCO destroys the stack and makes debugging harder. So therefore, trampolining can be used to simulate tail call optimization. The idea is when you reach a tail call, since there's no more to do in the function, you simply jump back to the start of the function with new arguments. This technique only works for tail recursive functions. The recursive call must be the last thing it does, and this heavily relies on garbage collection. And we can see the bottom example, so we're importing recursion tail call optimization from the FNPY module, which we'll look at a little bit more in a bit. But we basically see that we can call that function with something that would normally have exceeded the recursion limit. So lazy evaluation, so this is where we actually do the computation when results are needed. There are many benefits such as reduced memory requirements and saving unnecessary computations that may never be used. Lazy evaluation is a concept of objects that don't necessarily need evaluation or not evaluated. So here we call countdown, recursively, decrementing start, but we're yielding the result every time, so we just call .next, so it's not generating every value in that list. This kind of not quite lazy evaluation, but in functors we can use the LRU cache. So this is a decorator which wraps a function in the least recent used cache. This is form of memorization. Arguments of the function which are used to build a hash key, which is mapped to the result. So subsequent calls to with the same arguments will fetch the value from the cache instead of actually calling the function. So in this example, here we wrap the expensive function in the LRU cache decorator. We stipulate the maximum depth of loops and iterate through, calling the expensive function with various inputs. We can see the cache information, that there are no hits as we're calling the function for the first time with these inputs. We iterate through again, now with more values, and see that we print those we haven't seen before as the others are retrieved from the cache. So Python has built-in constructs to immediately facilitate functional programming. Lambdas help define an inline anonymous function. This is convenient for defining for immediate use or to assign to a variable, making it first class. This does not guarantee purity, however, so we can see we're doing a call to an outside function. And also we've seen decorators, which are an easy way to implement higher order functions, which can be used with the wrapper pattern. So map, reduce, and filter are 3 higher order functions in all pure functional programming languages, and we also have them in Python. Map provides parallelism by applying a function to elements in a collection, returning a new collection with new values. It doesn't have to be a lambda argument, we can pass in a functional name. The filter takes a predicate function and returns all the elements in the sequence for which the predicate was true. This can be achieved by list comprehensions, yes, so some deem this more Pythonic or readable or performant, but either way results in more succinct parallel code for iterating over constructs. So the employee example again, so we define an immutable data structure as input and then generate a new derived iterable. So we have no side effects, we do have code reuse, and we can have parallel computations. And then with reduce, so reduce takes a function and a collection of items and reduces it down to a single value. We can import it from the functools module in Python 3. We provide an accumulator variable and an iterable. X is the current item being iterated over, and A is the accumulator. So then reduce just walks over the items, and for each one it returns the lambda on the current A, and X and returns the result. And here we're iterating over the employees, pulling out the age value and providing a lambda as a first argument to reduce, to add each age to the accumulator as we iterate through the tuple. This again can be expressed as an inline. The accumulator can be collected of values appended and added to the collection, but this relies on the key in the collection being present. So we can just use collections and default dictionary, which can be used if the key doesn't exist, as one will be created with the type passed in. So multiprocessing and concurrent futures. So due to writing code in a functional way, we can parallelize our code easily by creating multiple Python processes and spreading out computation around CPU cores in parallel. It's very easy to parallelize when using map along with the multiprocessing module. So we just define our processing pool, and then we define the max tasks per child, so we can have things running concurrently. This might be a new way of looking at async programming in Python. We also have extra implementations to change how computations are handled in parallel. So using concurrent futures, we can either choose to run the code on different processes, in different processes, or using the same one in multiple threads. This brings up an interesting issue though, which is the global interpreter lock. So no two threads can execute Python code at the same time. Even with multiple threads, only one can execute at a time. This can cause blocking on threads when using I/O. To avoid this, so we basically use process-based parallelism. But as you can see at the bottom, it's really easy for concurrent futures to swap in and out with parallelism using processes and threads. So you just basically call processor pool executor or thread pool executor. So another library is itertools, which provides functions that are inspired by similar features in lazy functional programming languages. It implements a number of iterator building blocks inspired by constructs in APL and Haskell. There's just some examples. Then we have functools, which is a model facilitating use of higher order functions through partial application and wraps. Reduce can also be found in this module, as I said before. Then we have operator. The operator module is a functional alternative to add, subtract, etc. And we have a method caller, which returns a callable object that calls the method name on its operand, which you can see in the middle. Then we have FMPY. This supposedly provides the missing batteries to get maximum from a functional approach. So there's a bunch of Scala-inspired features, such as the lambda definitions, which are great, and persistent data structures and currying. And also Scala-style streams, which evaluate each new object on demand and share calculated elements between all created iterators. We also have the TCO decorator here, which is a workaround, like we said, for dealing with telco optimization without heavy stack usage. Then we have tools. Tools is a set of utility functions for iterators and iterators functions in dictionaries. It's made up of itertools, functools, and dictools, and they're basically pure lazy functions and facilitates currying and functional composition. Next we have Funcy. Funcy is a collection of functional tools focused on practicality. So it includes ways of manipulating sequences, decorators, and abstract flow control. And lastly, we have Coconut. So Coconut is a Pythonic functional programming language. It tries to provide the tools necessary for modern functional programming in Python. So valid Python code is valid Coconut. It claims that Coconut does to functional programming what Python did to imperative programming. And it runs on Python 2 and 3. These are just some examples of things we can do in Coconut. So we've got pipeline-style programming, lambda expressions, partial application, pattern matching, infix notation, lazy lists, tail recursion, parallel programming, and algebraic data types. And with compilation, You can use Python modules from Coconut and Coconut modules in Python. It compiles down to Python code. Like I said, it works in Python 2 and 3. It can't be considered purely functional, as valid Python is valid Coconut, and Python obviously isn't purely functional. So, to round out, using a combination of built-in and external libraries, many functional principles can be applied in Python. Pure functions lead to fewer bugs and easier to debug code. The repertoire of functional libraries and Python's dexterity make it a truly multi-paradigm language. Programs which use functional programming are usually shorter than the traditional imperative ones, but much more importantly, they're also usually more composable and provably correct. However, in Python, we can't enforce immutability. We've seen that we can utilize some immutable data constructs, but we can't define immutable variables. Also in the Lambda syntax that we've seen in FMPY and Coconut, there's different syntax possible, which would be great to utilize. And there's no support for pattern matching. But why should we care about all this? So we start by saying that object-oriented programming is orthogonal to other paradigms, but actually OOP and FP can coexist. So it means you can write object-oriented functional programs. Both can benefit from the features of others. So with polymorphism, the inversion of source code, and runtime dependencies, and also from immutability and not having concurrent update problems, leads to more safety in multiprocessing and multiprocessor environments. So ultimately, FP makes concurrency much safer, and FP is easy to write, easy to read, easy to test, and easier to understand. And if you are interested in looking into a bit more about functional programming, particularly in Python, here's some really good resources. So Top 2, Talk Python to Me and Podcast in It, great podcasts for Python, but specifically in regards to functional Python. There's a great series on Medium regarding the basics of functional programming. There's a really good YouTube playlist by Dan Bader on functional programming in Python, and then there's a Git repo for awesome functional Python resources. And that's everything. Thank you very much.